Hello, everyone from my side, and welcome to my talk on low power radio communication. So the presentation is structured as follows. I'll start with a motivation to the topic by showing the advantages of fully decentralized systems. Then I'll move on to the technologies where I will give you an overview of the current state of the art. Next, I'll focus on the optimization possibilities to reduce power consumption in radio communication, where I will go through several approaches on different levels. And two application examples then follow, one based on Bluetooth low energy and the other on LoRa. And finally, I will highlight the outlook with future research topics. So Eric already motivated this topic, but let me just give you another view to it. So our world is becoming an increasingly interconnected place. People, machines, objects, everything is more and more connected to each other. And to enable this progress, low power radio solutions are crucial. This development is additionally fueled by a shift from centralized to decentralized systems. So why are decentralized architectures and systems so interesting? So first, decentralized systems are really good when it comes to scalability. So we can easily extend in decentralized architecture with new nodes. We can easily extend the coverage area if we want to cover a wider area, or also easily extend the computational power by adding more nodes to it. Apart from that, also because of its redundancy, it is fail-safe, and we can easily replace units when they don't work anymore. Because we don't have also, as we don't have a centralized unit that controls the whole infrastructure, we have also no single point of failure and no higher infrastructure to rely on. So also points in security and privacy, but also as everything is processed on the edge, also low latency and minimal reaction times can be expected. Due to its decentralized structure, also it is modular and easy to reconfigure. Also from an efficiency point of view, because we don't have extra infrastructure. Also for low power, it is better, and we don't have also to send all the informations to the central node, so also a low bandwidth. Additional points are for example, cost and maintainability, but so this low power radio communication technologies enable this kind of architectures more and more. And this is the motivation for this topic. So let me just take a closer look at low power platforms. The talk last session showed a general overview of low power systems. When designing low power systems, a holistic approach is essential. And just to recap the last talk briefly, we have a core with a processor and memory where the functionality of the system is implemented. Here, the system operation is controlled and the data is processed, and this part is essential when it comes to low power, as everything is in the system is managed here. Around the core, we have the periphery with the sensors to capture the data we need, with actuators, some interfaces or outputs, for example, LEDs to give users a feedback. And also essential is the energy supply, the power management technique that affect also the low power radio communication. So in my talk today, I will focus on these three aspects on the core, where the processing also and functionalities are implemented, on the radio technologies, radio protocols itself, and on the energy aspect and power management. Okay, and last, there are also additionally the materials, the technology, the housing of the system. But it's not that important for the when we look at low power. So these three parts, radio, energy, processing memory, are inevitably belongs to this low power radio communication. Now let's dive into low power radio technologies. This chart shows different radio technologies. On the x-axis, we have the maximum range, and on the y-axis, the energy consumption. So we can see here, I clustered the data regarding their frequency band first. We can see the radio technologies in the 2.4 gigahertz frequency band. Some two most popular ones are Bluetooth Low Energy, which is popular and known from different consumer products, and of course Wi-Fi for internet connection. We have also in the 2.4 gigahertz frequency band different protocols that use the IEEE 802.54 standard, like Zigbee, that has become popular in the last years because of its use in home automation. And in general, we can say that these protocols can achieve a high data rate and can reach communication range up to 1 kilometer, but not more than that. And so here we have the main trade-off is between data rate and energy consumption. The second big family of radio technologies are in the 800 megahertz frequency band. So so-called wide area networks. The most popular ones here are LoRa and Sigfox. And these protocols can achieve a high range. They're optimized for high range. And so we have here a trade-off between range and energy consumption. So the third cluster are the cellular protocols, like, for example, NB-IoT. The special or the advantage of these protocols is that they can use the available cellular infrastructure and thus have a very good coverage. But the energy consumption is higher in comparison to LoRa or Bluetooth Low Energy. And we have some additional more protocols like ultra wideband or even NFC that have a small range that can also achieve a high data rate. Let me show you one second graphic. So here is another chart where we can see now on the x-axis the maximum data rate. On the y-axis we can see again the power consumption. So we can see here, as I mentioned also in the slide before, so the 800, the megahertz radio technologies, they don't have that high data rates. Their advantage are that they have a high range. They achieve high range, and the 2.4 gigahertz protocols have higher data rates, like Bluetooth Low Energy or Zigbee, Thread, just to name some of these. And when it comes to higher data rates, of course, Wi-Fi is mostly optimized to achieve the highest data rates possible in this frequency bands, and but also cellular technologies like LTE, but even also ultra wideband can reach very high data rates. So when realizing a system, it is important to understand that there are many trade-offs that should be considered. It is not possible to optimize all parameters at the same time. Here we can see the further the points are from the center, the better the property. For example, we have a system that is optimized regarding low power. This could lead, for example, to a decrease in performance. So when it comes to, for example, to signal processing, we don't have that much processing power. Or maybe using better components will lead to a higher price. For example, we also have to make sacrifices in terms of functionality. Maybe we could use, maybe we also, if you want to optimize, go one step further in the low power direction. We maybe could not use the highest security standards because it would lead to more redundancy in the communication and thus to more energy consumption. So I just wanted to, on this slide, to emphasize that there are always trade-offs that should be considered. And it's not possible to optimize all performance parameters at the same time. Now, let us look at the performance parameters of radio technologies. What should we take into account when selecting one appropriate radio technology? So first, one of the most important parameters is the range. So which areas do we want to cover with our applications? So for example, from a low power point of view, if you want to cover just an area of 100 meters, then it would be better to go, for example, with Bluetooth Low Energy than with LoRa, because in a very short time, in a very short burst, we can send all the data and go back to sleep mode in comparison to LoRa, where it would take more time to send the whole data packets that we collected. So it's always also here a trade-off. Then we have speed. How fast can the data be transmitted? Power consumption, of course, this is the topic of today's talk. Which frequency bands are used and are they licensed? One further point is the time delay of the system, the latency. Do we need, for example, for real-time operating systems, it could be very important to have a low latency in the system. Which topologies can be realized with this kind of technology? How many nodes can be connected with each other? If we want to scale the system and be able to connect several nodes with each other. Of course, in harsh environments, also robustness is a very important parameter, the robustness of the protocol. Also, here we have a trade-off. The higher the robustness of the protocol, the more redundancy we have in our technology. So the more energy it takes to transmit the information. So also the space that is needed. For example, the 2.4 gigahertz radio technologies need a smaller antennas than the megahertz technology. So if size is also a top, important requirement, then also that should be taken into account. Security, complexity, the availability of the chip in the market, and last but not least, of course, the price. So there are different performance parameters where we should look more into detail. And just to show you also some trade-offs, for example, looking more into details, the range. When we increase the range, it will go directly hand in hand with an increase of power consumption. Increasing the range will decrease, for example, also the data rate, or increase the latency. So we can see here we can't optimize all parameters at the same time. When increasing the speed, so the data rate, then also the range will decrease. When increasing the data rate, then the power consumption will increase. So it always depends on the power consumption. When we look at that in more detail, of course, increasing is the range, increasing the data rate, increasing the robustness of the protocol will lead to higher power consumption. Just to show some examples and to clarify that it's impossible to build the perfect radio technology and the perfect protocol. That's why we have so many different technologies on the market. So when it comes to optimization. So which points should be considered? So first, based on the requirements of the application, we should choose the best technology that fits. So regarding the range we need, the data rate, we choose a technology based on that. And then we can choose the best component. So we should compare different chipsets. In the next slide, I will show a comparison of 3 Bluetooth Low Energy ICs, where I will show you the power consumption for sending and receiving data. So this is another optimization point. Also, of course, after we have the component, the power supply should be optimized to have the best voltage level for this component regarding low power, to use power management techniques to further also here optimize the current consumption. Next, on the radio protocol level, so each technology has also a standard behind it, a radio protocol. So here, depending on which one we choose, we can optimize different protocol parameters. So most obvious one to optimize the power consumption is the output power. But yeah, there are many others. The data rate could be optimized if we don't have to send that big amounts of data, then it would make sense to use other modulation techniques that are more robust, that allow us to further decrease the output power. But also we can think of using adaptive algorithms that optimize the protocol dynamically at runtime. On the application level, also this depends on the requirements of the application. We can choose the duty cycle we need. We can and we should bring the system as much as possible in sleep states, and we can also reduce, for example, the data to be sent by sending information instead of just of raw data, directly signal processing on the edge, or by data compression, for example. So all these points helps to optimize our power consumption when it comes to low power radio communication. Yeah, just one example, without going here into detail and reading all these data sheets, but just to give you one example. I also didn't have chosen the best chips for from each company. I just choose 3 examples just to have a comparison. So here, for example, one Bluetooth radio chip from TI that has a current consumption of nearly 20 milliamps when receiving and 24 milliamps when transmitting. In comparison to that, here another chip from ST. It needs 7 to 8 milliamps to receive and 8 milliamps to send. And yeah, last but not least, one chip from Nordic Semiconductor, which needs 3 milliamps, around 3 milliamps to send and around 2 to receive. So just want to show that it's really worth it to compare different. So although we have chosen the same technology, which has the same radio protocol, also the components here are really important. So we can summarize that for this optimization, the perfect technology or protocol doesn't exist, but there is for your application with your requirements one best approach. So we first have to determine the most important parameters for our use case and weight them, and based on that, choose the best or identify the best technologies, the best protocols, the best components, and so on. Just let me give you two short examples. So here, Bluetooth Low Energy. So it's a protocol in the 2.4 gigahertz frequency band, ISM band. It uses 40 channels with 2 megahertz spacing. So that's why Bluetooth Low Energy is very robust, and it uses frequency hopping in this 40 channels to achieve this robustness. That's why we can use also Bluetooth Low Energy in very crowded places, and it still works. As a demodulation, it uses frequency shift keying to modulate the bits in the radio signals. We can achieve data rates up to 2 Mbit per second. But yeah, there are different, on a file level, different data rates we can choose. For example, also coded PHY was introduced with Bluetooth 5, where we can also have higher communication ranges, but for example, with the trade-off that we have lower data rates. Okay, so yeah, apart from that, here on the right side, you can see different topologies. The most popular one is a point-to-point communication, also known from different consumer products and smartphones. This is a standard way for Bluetooth communication, but also there are different other possibilities for topologies like broadcasting. It's where we can broadcast information, and each node that can receive the information will receive it. And also there are possibilities to build a mesh with Bluetooth Low Energy. Yeah, one feature of Bluetooth, just one additional point, is that it has also different positioning features. So one platform we developed based on that is the sensor actuator platform Swarmy. We use it, for example, for condition monitoring for industrial application, where we build decentralized, distributed sensor networks, also synchronized, where synchronized measurements are performed on different locations. So this is the Swarmy platform. Just to give you here some impressions, we achieved a communication range of 1 kilometer, of course, with low and very low data rates, but just to have an idea. And yeah, so here also a small specification. I won't go into detail, but yeah, many different sensors are integrated on this platform. We have also analog and digital interfaces to be able to be modular and able to connect a new sensors to this platform. Also, actuators are here integrated. Mainly the communication is done via Bluetooth Low Energy, Bluetooth 5. Yeah. So the second example is based on LoRa. So LoRa is a radio technology based on the megahertz frequency bands. So it depends on if you are in Europe or in Asia or in North America. There are different regulatory for that. Here in Germany, we have the 868 megahertz. And yeah, LoRa achieves its high range because it has a very robust modulation technique called chirp spread spectrum, and the spreading factor can also be configured. we have different N and decodings to achieve a robust protocol. The data rate is up to 50 kilobits per second, and yeah, the typical LoRa network consists of end nodes. They communicate directly within gateway, and the gateway will transfer the data to a server where we can see the information. So point-to-point communication is possible. Star and star of stars topologies are here, can be achieved. So LoRa, just to clarify, LoRa is the PHY, the physical layer of this technology, and LoRaWAN is the MAC layer, so the radio protocol behind it. And also one example here. So we developed a system called Astrose for power line monitoring, powered by energy harvesting. We measure different properties of the line, like the temperature, the current through the line, the inclination, and the swing, and in different projects also some more informations. And here we transfer the data using proprietary chain topology that we developed based on LoRa. So to achieve this a low power communication, as we don't have that much energy in the system, and as we need high ranges of communication. So here the nodes are 5 to 6 kilometers apart. Okay, so now I will come to the end and give you an outlook. What are the next steps for ultra low power radio communication? Where will be the next research topics? So, of course, power management techniques could further optimize the energy consumption. Here are some more research areas. We have also in our group a research regarding adaptive algorithms to optimize the energy consumption at runtime instead of using static configurations. So I think this will be a big topic in the future. Also that the standards and radio protocols will provide it directly, so that it is integrated directly in the standards. Also machine learning approaches where machine learning is directly performed on the edge, but also better routing approaches when it comes to long-range radio protocols and networks. Yeah, then thank you for your attention. And yeah, I'm happy to answer your questions.